Intermediate Algebra, Section 9.6, Solving Logarithmic Equations. Certain logarithmic equations can be solved by writing an equivalent exponential equation. It's essential that we remember the properties of logarithms that have been previously covered. So consider reviewing those properties before attempting to solve equations similar to the ones we're going to go through. So here they're asking us to solve this equation. It's logarithmic. Translate it into an equivalent exponential. It would be the base raised to the third power is equal to x. We're virtually done, other than simplifying 4 to the third power, 4 times 4 times 4. Our solution would be x is equal to 64. In this next example, it worked so well in the last one. Let's translate this exponent or logarithmic equation into an equivalent exponential form. And remember, ln is shorthand for log base e. So transforming this, we would have the base e to the fifth power is equal to 3x minus 2. Solving for x, we'll add a 2 to both sides. So we have e to the fifth plus 2 is equal to 3x. And to undo multiplication, divide both sides by 3. It's oftentimes important to have the exact answer, so we'll leave this with e rather than putting an approximate value. And problems often ask you to leave your result in an exact form. Looking at another example, here's where definitely the properties come into play as far as simplifying a problem. We have a difference of logs, and a difference can be expressed as a single logarithm as long as our bases are the same. There aren't any bases, so it's understood this is a common logarithm with base 10. A difference is equivalent to the quotient of those quantities. So it'll be the first term over the second term is equal to log of 3. Using our principle of logarithmic equality, if we have logs with the same bases equal to one another, the quantities then must equal one another. And solving this, we've got a rational equation now, recognizing x can't be a 5 because we would have an undefined expression, so we have a restriction on our domain. We also have to keep in mind that we can only take logarithms of positive numbers. So when we get solutions, we have to be on guard for several possibilities of not having a variable generate a 0 in the denominator, and also that whatever our variable is to the solution, that we not end up with a negative for this example, in either of these cases. So let's get rid of the fraction or the rational expression by multiplying by that denominator. The x minus 5 cancels out on the left, leaving a 5 plus x. On the right, distributively, we have a 3x minus 15. Putting the x's on the left, I'll subtract, or on the right, I'll subtract an x, and the constant terms on the left, so add a 15. We end up with a 20 on the left, a 2x on the right, divide both sides by 2. We end up with x is equal to 10. Is that going to meet the criteria that we can only take logarithms of positive numbers? Well, 10 in place of x here would be the log of 15. That's fine. 10 minus 5 would be the log of 5. So this is going to check, and we can plug it in to verify that it is a true statement. In this next problem, very similar to the last one, we have a difference of logs, so we can combine them into a single log from the property of quotients of the first term as the numerator and the second term as the denominator. We now have a single logarithm equation with an understood base of 10, since it's a common logarithm and no base is written. Exponential equivalence would be 10 to the second power this base to that power is equal to this quantity. We have a rational equation like the last one that we'll want to multiply by the denominator value on both sides to eliminate the fraction or the rational expression. 10 to the second power is 100, that will distribute, so 100 times x, 100 times 2. The denominator cancels the value that we multiplied by, leaving an x. Getting our x's together by subtracting an x from each side, we end up with 100 minus 1, or 99x, plus 200 is equal to 0. Taking the 200 to the other side, or subtracting 200 from each side, gives us a negative 200. And finally, solving for x is a negative 200 over 99. As far as simplifying this any further, there's a problem. Regardless, we have a negative divided by a positive, the result will be negative. And here, there's nothing that will alter that sign when we replace x with that negative, and this fails for the condition that we can only take logarithms of positive numbers. So we will reject that value as a possible solution and say that this equation has no solution. A couple other examples. Here we're given a log with no base, understood to be a common logarithm of base 10. To solve a logarithmic equation, transform it into exponential. So it would be 10 to the 2/10 is equal to x. And a matter of just raising 10 to the 2/10 power using your calculator, you should find a 1.58 is equal to x. For a check, just to illustrate that, we would be taking the common logarithm of our x, which is 1.58, and testing to see if we get a 2/10. So using the calculator, the check is taking the common log of 1.58 is the result equal to 2/10. And again, because of rounding and approximation, we would round this to 1/2. Our 0.19 would be, to the nearest tenth, would be 2/10. So we're satisfied that we have a correct solution. So it's always a good idea to check to make sure that the solution is correct. In this next one, we're given a logarithmic equation, translate it into an exponential equivalent. So we take our base to the second power is equal to the quantity we're taking the log of. 3 to the second is 9. Solving your equation for x, we'll subtract a 5 from each side, leaving a 4 and a negative 2x. Dividing both sides by negative 2 leaves us with a negative 2 is equal to x. This doesn't look good because of the negative, but notice where the place of that is. We would have, as a check, we would have log base 3 of 5 minus 2 times negative 2. I guess I should put a bracket there and test to see if it does, in fact, equal 2. The negative times the negative is a positive, so we would end up with a positive 4. 5 plus 4 is the log base 3 of 9. Does it equal 2? Well, let's translate it into exponential form. The base to this power is in fact equal to 9. So although initially a little suspect in the fact that our x was negative, but because of the placement of the variable, it was fine to have a solution with a negative. It's when it's put in the equation and results in a negative that we have to reject it.